Good evening, everyone. Welcome back to the week 8 live session. So, today we will be covering certain topics regarding oligomerization and polymerization. And at the end of the live session, we will be taking up some problems so that you can use your concepts and apply onto it. We will wait for 2 to 3 more minutes for others to join. And if you guys have any query from the previous sessions, you can unmute yourself and ask the question, or you can put your question in the chat box. I'll be happy to answer it. So within short span, we'll start the session. Thank you. So the topics that we are going to cover today, week 8 and so we will be talking about ethylene trimerization, the catalyst involved in this one, and the mechanism. Followed by we will be talking about propylene dimerization. Third would be your cyclotrimerization of 1,3-butadiene system. And at the last, we will be talking about olefin polymerization, which is having different types of materials: thermoplastic, duraplastic, and elastomers. And ultimately, assignment. So these are the things that we are going to discuss today. We have generally generally in last live session we ended up talking about alkene and alkyne oligomerization where nickel hydride was the main species. So I'm taking a general point over here, alkene and alkyne oligomerization. So this has been further taken into picture and classified as the main topics: ethylene oligomerization. That means the substrate here is your ethylene molecule. Second is the ethylene trimerization. Third one, the way I've just written over there, propene dimerization. And the fourth one is cyclotrimerization of 1,3-cyclobutadiene. So this is actually the main generalization where we have already taken this first topic into picture in our previous slide, where we have converted the ethylene into different alpha olefins and oligomers, where the nickel hydride has considered to be the active species. So here in this case, nickel hydride was the active species. And if we are changing some solvent, we will be ending up having more molecular weight. And if we add the PPH3. So it will terminate your chain. So for termination, we need to add this group. So this we have already taken in previous session. Now the today's topic we will start with. It's your ethylene trimerization. Which means that this is your ethylene molecule CH2 double bond CH2, and you're taking 3 molecules of it, and it is getting trimerized to give you 1 hexene. So this is your ethylene. It is undergoing trimerization and giving you 1 hexene. So it is stopping at over here. It is not going into a long chain. That's why the ethylene trimerization, we can stop the reaction at this place. So here, in this particular reaction, there are some features which we need to know. First is quite high selectivity is being observed in this reaction, because we know that only one kind of product, one hexene, is being forming over here. In first case, ethylene oligomerization, we were using the nickel catalyst, and nickel hydride was the active species. Here, a tantalum-based catalyst is being used instead of the nickel one. That is a composition of tantalum chloride with any metal alkyl, where this um, so it's 5, and where MRN would be your trimethyl aluminium, tetramethyl tin, etc. So there are certain different alkylating metal alkylating agents. So how the reaction actually proceeds? We have tantalum pentachloride, and when it is reacted with MCH3N, this is your alkylating agent, and this will take up 2 chlorides, metal and chloride would go out, and tantalum would come as 3 chlorines connected, joined with tantalum, and 2 CH3 groups would come and intact with tantalum. Still, it is maintained its +5 oxidation state. -3 is coming from taurine, and -2 is coming from 2 methyl groups. Now, at this position, we are introducing first uh, ethylene group. So what it will form, the chloride remains as such, and if one CH3 is like this way, other CH3 is this way, so it would coordinate, and firstly it would coordinate, and then it would undergo the insertion into the metal alkyl bond. So here you have the metal, anything could be possible. So insertion into the metal CH3 sigma bond, and ultimately what it will form, it would be giving us Cl3 would remain as such, tantalum, and it would form alpha, beta, and this CH3, and the other CH3 remains as such. Now, since it is having a beta hydrogen, this will go here, and it will, if I'll draw it in other slide, okay, ultimately it will then form Cl3 tantalum, since beta hydride hydrogen elimination has happened. So the hydride will come over here, and the alkyl group, on release of the hydrogen, beta hydride, on release of the beta hydride, it would form an alkene, which will again coordinate with the tantalum as a pi interaction, and the CH3 will remain as such. Now, if you'll see, it is again in this +5 oxidation state, in +5. So it has a tendency to undergo reductive elimination. And reductive elimination, we know that it would release your methane group, and ultimately it would form Cl3. Also, it would release your this propene and Cl3 tantalum. So this is in +3, and this actually is your active species. So firstly, we are showing the mechanism to make the active species, which is going to convert your ethylene into a 1-hexene. I hope you guys have understood it. I'll just repeat it one more time. So what this reaction says, we are taking the ethylene molecule, 3 molecules of ethylene, and it is converting into 1-hexene. So in this case, we are using tantalum pentachloride with an alkylating agent. So we need to make an active species, and the active species is the tantalum +3. So how do we make it? Firstly, the starting salt is tantalum tetra pentachloride, which is which is being made to react with alkylating agent. It could be anything. And after that, two of the chlorides would go with your metal, depending upon the oxidation state of it. So only two will go out, and rest of the coordination number would be uh, fixed from the alkyl. So two of the alkyls will come into the picture, maintaining the oxidation state. And now when it is +5, we are introducing the alkene over here. So the alkene could only be coordinating with this one as a pi interaction, and the two alkyl groups remains as such. Now when we have a metal alkyl, that means metal C or metal hydride bond over there, then alkene tends to insert into it through alkene insertion into the metal carbon bond. Once it is being formed, so it is 1, 2, and 3, it would form a linear chain and having a sigma bond with the tantalum. Now, if you'll carefully see here, we have the carbon which is directly connected to the tantalum that would call as alpha. Adjacent to that is called as beta. And whenever we have a beta hydrogen, it would definitely go to a beta hydride elimination. So this step is your beta hydride elimination. And once it is done, then the hydride would come and connect with your tantalum, and the alkyl, which was there in linear chain, it is then being formed as an alkene. Earlier it was a sigma bond, now it is a pi bond. And since we know that this pi bond can easily be, this is just a pi interaction, and already tantalum is in +5, so it would undergo a reductive elimination to release the methane as well as propene, and it would form your active species as tantalum and +3. Now this +3 state would undergo to make the trimer product of your uh, ethylene. So if you will see the different features of your tantalum trichloride, it is sterically as well as electrically unsaturated, which means if you will see the coordination number can easily go from +3 to +5. So it is having a coordination number of 3, so it can go to 5. Also, it is having an oxidation state of 3, it can go to +5. So both electrically as well as the aesthetically, it is unsaturated. Also, if you will count its total electron, chlorine minus would give you 2 electrons, and one tantalum in +3 would give you 2 electrons, right? Tantalum belongs to vanadium group, and in vanadium, we know there is 5 electrons, and when you are taking the 3 electrons from there, only 2 electrons are left. So therefore, this is giving you 2 electrons, plus 2 electrons are coming from each chloride. This would be a 18 electron species, right? Now, how the mechanism works in case of ethylene trimerization. So we have got to know that this particular species, Tantalum trichloride, it is my active species. Now we will start the process. From here, when I'm introducing two ethylene molecules at this stage, firstly, those two ethylene molecules, they will undergo oxidative addition in a way that if we have a tantalum 3 chloride, there is one alkene. So they would form an oxidative addition product like this way, and it would ultimately be forming a metal metallocyclopentane kind of derivative intermediate. And now see, it is +3. Now it is going to +5. That is why we are saying it as an oxidative addition. Two of these alkenes, ethylenes, they are connecting and they are making this kind of intermediate. Now, if we will introduce a one mole, this third molecule of ethylene, it will again increase the chain because it would undergo an insertion. So this would be an insertion step, and this goes from 5-membered ring to 7-membered ring. Okay, now this is a 7-membered ring, oxidation state being +5. Now again, if you will see over here, there is alpha, there is a beta, and it is having a hydrogen. Again, this will attack over here and this will go here. What we will be tending up forming tantalum hydride, and the other species would be, this would be in pi interaction, and ultimately okay, this is another side. So only one side is open and the other side is having. So now this is CH2, this is hydride. And once reductive elimination is happening, we will be ending up having this particular one hexene, and it will regenerate your active species. I hope this has been clear. So firstly, if we'll see the first step, that is involving two molecules, two ethylene molecules, which is undergoing oxidative addition, and it will form a 5-membered metallocycle kind of intermediate. Now, when I'm introducing the third, this is third ethylene, and when I'm introducing at this particular step, it would insert in the metal and carbon sigma bond. After insertion, this 5-membered ring becomes a 7-membered ring. And this in this 7-membered ring, we have a alpha position, we have a beta position. The beta hydride position, this would undergo a beta hydride elimination. And once this is formed, it would form a tantalum hydride and the cyclic product would open up. Now we know that it is in +5 state. It can easily go to the +3 because of the reductive elimination. So this group and this whole alkyl group would go and make a 1-hexene as your final product and would regenerate your active species. So this is a very simple mechanism if you have understood properly. So I would just write here what are the steps that we need to remember. So the first step that we have is the oxidative. The first step that we have is oxidative addition of two ethylene molecules to your active species. And then second step is it would form a 5-membered ring. Then we can say the coordination and insertion followed by insertion. ordination and followed by insertion of third molecule of ethylene. So two molecules we earlier used and third molecule is being used here. So to generate a 7-membered cyclic metal cyclic ring. After that, it would follow up beta hydrogen elimination. And then last step is your reductive elimination to give the product and the active species. So these are the steps which are very, very important, which is happening at what point. So this trend you have to understand, you need to practice this again and again. So I hope you have understood this. Now we will move to our next topic of the today's discussion, which is propene dimerization. So what we saw earlier, that was ethylene trimerization. Now we are going to see how propene dimerization will happen. So here the process in which propene dimerizes and gives what would be your product expected product, branched hexanes. Since we are talking about dimerization, so propene is a 3-chain molecule. So after dimerization, it should be having only number of the carbon as 6. So it would give you branched hexanes. And this process is called as dimersol process. The name is also important. Please remember this. So this process where our substrate is propene and it is giving us branched hexanes. This process is called as dimersol process. So we will see how this process works. So what are we saying? That we have a propene, and if I'm taking, say, for example, 2n, that n can be any multiple, where n is equals to x plus y plus z, 2n is equals to x plus y plus z. Why we are writing like this? So in presence of the catalyst, it can give us x number of this particular product, and second branched product like this way, and z number of. So there are expected 3 particular things where we would be seeing like at what step what is forming. Okay, so let's start with the mechanism part. So in this particular case, we again use a nickel catalyst where we have a nickel where L is equals to your PR3 phosphine group and X equals to X is your ethylene yeah. So it would be this kind of species where it's in positive and that is negative. So this would be forming as your species. So we have a propene, which is the double bond is in delocalizing all the 3 carbons. So here we are starting with, because it is a pi interaction, so it is having the charge from only the, it is in plus 2 oxidation state. So this also can be written as nickel attached with L and X, and it is forming a sigma bond and it's having a pi interaction with the alkene bond. Now what we are actually understanding here, if we have a nickel and now we were saying that it was having like this way. If I'm introducing a propene molecule over here, then it would definitely come and coordinate with your nickel species because of the pi interactions, and the other bond would be having a sigma interaction. Moving ahead, now firstly what will happen, this will, because this is an alkene and this is the M metal carbon sigma bond. So firstly, the insertion will be happening of the alkene to the metal carbon bond, and followed by coordination of another propene molecule. So what it will give us, L nickel X. I'm saying that I have introduced this coordinated molecule, and the other one, this would, when it gets inserted over here, what it will be forming, it will be forming this kind of branched alkene, and it is connected still as a sigma bond. Now if you will see here, it is alpha beta, and this beta is having hydrogen. So we will be ending up having, so what we will get here, it would, it will give you nickel, since hydride has been formed, L and X, and there was a propene molecule already connected, that, and it has released this species. So one such species has been generated over here, which we thought of that it would be coming. Okay. Now here again we are saying that coordination of a propene molecule. Firstly, it would this one will insert here, this would be inserting here, and this would coordinate. So what it would be forming, nickel X. So when this inserts here, this would be giving this branched, and new propene is here. Now we have another one. So this, again, this will coordinate, and this will insert, and this will coordinate. It would continue to form the structure like this way. What we have formed is nickel X. This is alpha, this is beta. It would give you your product, and could release L nickel hydride again. So the main point is that our active species is this one, and if you will see that this was the structure that we were forming. So to generate the active species, we needed the propene, and ultimately we were having 2N molecules we have used, and it has generated our product over here and the last product over here, and the active species continues to be formed. So in this particular case, there are certain features that we need to highlight. So as I said, the active catalytic species is nickel hydride species, and it has been seen that, as I said, it is having an X group, it is having a PCY3, and also certain charge coming from, because this would be a whole group, and this is having a prop. So this starting catalyst that we have used it shows a turnover frequency around 60,000 per second, and it is comparable with 1 lakh turnover frequency which comes from an enzyme. So its reactivity is very comparable. So it is highly active species, which we have seen. And here also we have realized what are the steps. Firstly, we will be having a substrate catalyst over there, and it would be generating our active species, which is this one. Once the active species is generated, then it would continue to react with two molecules of propene, and ultimately after beta hydride elimination, it would give you the product and the active species is regenerated. And these are the following features. Now, next that we have in hand is cyclotrimerization of 1,3-butadiene. So now we have 1,3-butadiene, and how the cyclotrimerization product would look like, that we have to look into. So here also the species that catalyst that we are considering is the nickel based. So it's in +2 state. And firstly, when we are using two molecules of ethylene 1,3-butadiene, it would do the reduction elimination. That means these two groups, they would eliminated as this one, and it would connect with your 1,3-butadiene as a pi interaction, and it's in 0 state. So reductive elimination starts from +2 to 0. It went to 0. Now, since this is your species, so you have nickel, in 0 state. Now we are introducing 1,3-dibutadiene. So this will undergo oxidative addition because it is in +0 oxidation state, so it can easily go to +2. So if you will see clearly, you have two molecules. So these will undergo the oxidative addition, and this would just coordinate with it. So how it will form? This is your nickel, and so again we have, so this is in +2 now because it has been a kind of a cyclized product. Now at -40 degrees, greater than -40 degrees Celsius, so this whole group would undergo a, a rearranged product, which would be like 1, 2, 3. So this would form a nickel. Again in +2, it's just a rearrangement. And then when reductive elimination happens at greater than -40 degrees, now the whole thing would again rearrange to form a nickel 0 species. And these 5 bonds are like this way, which would connect with your nickel. Now, when we are introducing two more 1,3-butadiene. So what it would be doing, it would release the trimerized product. So this is your product, and it would regenerate your active species, nickel 0. So this is active species and it is regenerated, and this is your product. Therefore, how the cyclic trimerization is happening by using the 1,3-butadiene, and what are the highlighting points that we have in hand. So the first one is our pre-catalyst is nothing but your nickel in +2 state with allyl groups. Then here the nickel oxidation state has been changed from 0 to 2 and vice versa. And also the coordination number has been seen to be changed from 3 to 4. Also, this kind of system is called to be as a naked nickel. And this naked nickel in nickel 0 is stabilized by the pi donor ligands that we have seen over there. And this particular process, if we have to carry out industrially, then there we have to use Ziegler-Natta catalyst. So these are the important things. So how it works in industrially. So if we are having 3 molecules of 1,3-butadiene, we know Ziegler catalyst is titanium tetrachloride with R2Al2Cl3, and it would form a cyclic group like this. Which on hydrogenation, so this is just a hydrogenation step, it would give you a hydride product, and then on treatment with oxygen and second treatment with nitric acid, it would open the chain to form, since it is 12 number, so CH2, and the other one will become COH and COH. So this is your industrial application. So this was your trimerization. If we have to Okay, so we have seen the cyclotrimerization of 1,3-butadiene. What about cyclodimerization of 1,3-butadiene? So what would be the possible product, and how do we uh, control it. So again, the starting catalyst would be your allyl groups in +2. So we are using 2 molecules of unsubutadiene, and here in this step we have added the phosphine group as well. Now, after reductive elimination, we know that what would be the product. So this group will go, and ultimately we will be having this kind of system. It's similar only with respect to the trimerization, but the only difference is now we have PR3. So the first possibility that it would undergo the reductive elimination to give you COD product. Cyclic octadiene. So these two will combine together to give you this one. The second possibility, if it exists like this way, the nickel, one of the two allyl bonds, if they form the sigma bond and the other double bond is outside. So if this is the scenario, after reductive elimination, it would be forming 1, 2, 3, 4, 5, and 6. So it would form a 6-membered ring. So this is your another product. Or if it exists as this way, a cyclic, metacyclic penta intermediate with 2 bonds outside. And now if this exists, so after reductive elimination, it would form 1, 2, 3, and 4 product with alkene groups outside. So these are the 3 different possibilities we get when we are doing the dimerization of butadiene in presence of PR3 group. And now the last topic of our discussion, which is olefin polymerization. So in this, we have first one as thermoplastic materials. Second, we have duraplastic materials. And third, we have elastomers. So the first one, thermoplastic material. What are their features? So their feature is they exhibit, they have shape stability under short-term strain. However, when we give slight heating to it, they transform into plastic. And plastics does not have memory. So they can't memorize which shape they were in earlier. These materials are built from linear or slightly branched polymers with low segment mobility, and their working temperature has to be lower than melting point for crystalline materials, or it has to be lower than glass transition temperature for amorphous. So these are the features that we have with thermoplastic, which they exhibit very uh, at very low strain they exhibit shape stability, but on warming they convert to plastics. Uh, Also, they have their working temperature is lower than the melting point in the glass transition temperature. Then we have second one is duraplastic materials. So these materials, so they maintain their shape. Matlab they have the shape stability upon extended period of strain. Even if you give a strain for a long time or under high pressure, they will high temperature, they will remember and they will maintain the shape. They are formed from pre-polymers such as rubber through thermal cross-linking process. So this process is irreversible. So they are formed through cross-linking process. Second, they also have low segment mobility and they are rarely crystalline. Most of the times they would be formed seen as the amorphous material. And the last among the all elastomers. So they are being used or applied above the glass transition temperature. They are deformed through application of force. Force. However, they have memory and they can store back if the stress has been removed. That's the specific feature of the elastomers. They are formed by cross-linking long chain polymers. And they are the one which exhibit high segment mobility. So these are the difference in different materials which has been formed from olefin polymerization, thermoplastic, duraplastic, elastomers. These two have low segment mobility. This is having high segment. This is having memory effect, which both of them they are not. This can be deformed in slide. This has shape stability for a very small time and in small strain it can remove its it can get D-shaped, whereas duraplastics they can retain their shape under high temperatures as well as extended strain, whereas elastomers if they are deformed by the force and if we remove the force they would retain their original positions as they have the memory effect, and this is the clear justification of it. So with that, we have covered all the topics of the week 8 session, and now we will quickly take up the assignment questions. So here we have, it says that product of the following reaction is or are. So you need to identify which one is your, this is your substrate. So your substrate is your ethylene and 3 has been used. And we know that ethylene trimerization gives you which product? It's 1-hexene using this catalyst where your active species is tantalum trichloride in plus 3. So out of the 4, we have this 1, 2, 3, 4, 5, and 6. So this is your 1-hexene and this is your product. You can try by yourself to do the mechanism, how it works, and then you will get to know about the answer. Now we know that the substrates of the dimersol process, dimer is there. So dimerization of propene we have seen, and that is called as dimersol. So the answer is D. Now this is also very straightforward. The turnover frequency when we are using this nickel allyl based catalyst in dimersol process. So we have seen that it reaches up to 60,000 per second, which is 6 into 10 to the power 4. So the seconds is common over here. Only the option C is 10 to the power 4. So this is the right option. The catalyst which is being used for the following reaction is. So we have here, this is nothing but your 3 molecules of 1,3-butadiene, and it is giving you a trimerized cyclic trimerized product, and this is possible when we are having a nickel allyl catalyst. So nickel allyl catalyst is your, it's the one which is actually working, doing the reaction. Now when we have the major product of trust, the same question of the 1,3-butadiene, when it is undergoing cyclotrimerization with this nickel catalyst, what is the product? And if you will be smart enough, if you'll see, this is your product and this is a trans one. So this highlighted one is the trans thing. So this is also trans. This bond is also trans and this is also trans. So therefore, all the three are 159. If I am starting with this, any one bond you can start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So where we are having the double bond at 1 position, 5 position, 9 position. So all are trans, trans, and trans. So that's why the answer is your trans, comma trans 159 cyclododeca triene. So this is your major product. Now it has been asked that the falling intermediate, which is symbolized as 1, formed during the cyclotrimerization of 1,3-butadiene occurs how? So we have this product, we have seen it. So this is actually called as naked nickel, which is in zero oxidation state. So is it a concerted 2 plus 2 plus cyclization, or it forms from its intermediate species shown below? So we have also actually seen that this intermediate has been seen during the mechanism of this reaction. If you will just revise what I have taught today, you will get to know. So by the reaction of 6C2H4 and C2H2, no, this is not right. So only the option B is correct over here. Now we have, it has been asked that this is the reaction and you need to identify the intermediate of it. So this is nothing but your uh, cyclic product, which is a cyclotrimerization of 1,3-butadiene And this is just, we have seen that it is a 1,5,9 trans dodeca triene. So this we have just seen. But this kind of reaction is happening in presence of Ziegler-Natta catalyst, that too industrial application it is. So under presence of hydrogen, it is giving us a hydrogenated product which on oxidation and in presence of HNO3, it is making a carboxylic acid. So only possible in presence of hydrogen, all the double bonds, they would get reduced to make a single bond. So the only option that we have is C, which can only give you this kind of open chain acid group. So the option is C. Now we have the products of the following sequence of reaction either are. So here you can see this is dimerization of 1-butadiene, which we have just read. And here is the nickel allyl catalyst in presence of PPH3. So this is your reductive elimination step, which goes from +2 to 0. And here it is binding with your 1,3-butadiene. Now, if this is your possibility, we have seen three particular possibilities. If this is your possibility, so the two bonds that are connected to the nickel on reductive elimination, they both get connected and they would give you a four-membered ring. The dots will connect together and here you will get your product. So out of the four, only the A option is the right option. So the segment mobility of the polymer depends upon what? So it is actually dependent on the cross-linking of the polymer. So whether it is low or it is high, it depends upon how much cross-linking is happened. And the materials that exhibit shape stability under short-term strain is also known as duroplastic materials. So this is the assignment that we have taken into consideration. So these are just the practice problems, and with this one you will get an idea how to solve the assignment questions, which are quite different from these, but you will get to know how you have to use your concepts in solving the problems. So with this, the topic from my side is over. And if you have any doubt in understanding any concept, you can just unmute yourself and put your question across. I would be happy to answer if there is any particular doubt you have. Thank you for joining me.